When dealing with motor circuits, proper overcurrent protection and conductor sizing are critical for safety and code compliance. For a 2 horsepower, 230 volt, 12 amp single-phase repulsion start induction run motor, several factors must be considered. Let's break down the process step by step. Firstly, we need to determine the branch circuit overcurrent protection. According to NEC 430.53 C5, the maximum overcurrent protection for this motor is 25 amps. This means that the breaker or fuse protecting the circuit should not exceed this value. Secondly, we address the running overcurrent protection. For this type of motor, a repulsion start induction run motor, running overcurrent protection is not required. This is detailed in NEC 430.53 C2. Now let's move on to the branch circuit wire size. To determine the appropriate wire size, we reference NEC Table 310.15 B16, which provides ampacity ratings for insulated conductors. This table assumes conductors are rated 0 to 2000 volts. For a copper conductor with 60 degrees Celsius insulation and considering a 125% load factor, we can determine the appropriate wire gauge. Assuming a 125% load factor, we multiply the motor's full load current of 12 amps by 1.25, which gives us 15 amps. For the circuit conductors, using copper wire with a 60 degrees Celsius insulation rating, a 12 American wire gauge conductor would be suitable. If using aluminum conductors for the circuit, a 14 American wire gauge conductor would be needed. For the motor leads, a smaller gauge wire may be acceptable due to the shorter length and different operating conditions. However, it is still crucial to adhere to NEC guidelines and ensure the wire is appropriately sized for the motor's current draw and temperature rating. For copper motor leads with a 60 degrees Celsius insulation rating, a 10 American wire gauge would be suitable. If using aluminum for the motor leads, a 12 American wire gauge conductor would be needed. It's important to note that these calculations are based on general assumptions and standard NEC practices. Always consult the specific motor nameplate data and local electrical codes for any additional requirements or exceptions. Factors such as ambient temperature, conductor bundling, and voltage drop can affect the appropriate wire size. Remember to always prioritize safety and consult with a qualified electrician for any electrical work. This information is for educational purposes only and should not be considered a substitute for professional electrical advice. By following these steps and consulting the relevant NEC articles and tables, you can ensure the proper overcurrent protection and wire size for your motor circuit, contributing to a safer and more efficient electrical system. Consider other factors when selecting a wire size. Firstly, the ambient temperature around the conductors. NEC Table 310.15 B16 provides ampacities at a specific ambient temperature, typically 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature is higher, the conductor's ampacity must be adjusted using correction factors found in NEC Table 310.15 B2. Secondly, consider the number of current carrying conductors in a raceway or cable. When multiple conductors are bundled together, their ability to dissipate heat is reduced, which lowers their ampacity. NEC Table 310.15 B3 provides adjustment factors for the number of current carrying conductors. Thirdly, consider voltage drop. Excessive voltage drop can cause motors to run inefficiently and can damage equipment. NEC Informational Note Number 2 to 210.19 A1 and NEC 215.2 A3 recommends limiting voltage drop to 3% for branch circuits and 5% overall for feeders plus branch circuits. To minimize voltage drop, you may need to increase the conductor size. To calculate voltage drop, use the following formula: voltage drop equals 2 times K times I times D divided by circular mils, where K is the direct current constant, which is 12.9 ohms circular mils per foot for copper and 21.2 ohms circular mils per foot for aluminum. I is the current in amps, D is the one-way distance of the circuit in feet, and circular mils is the area of the conductor in circular mils, which can be found in NEC Chapter 9, Table 8. Fourthly, consider the conductor termination temperature rating. Equipment terminals such as breakers and motor terminals are often rated for a specific temperature, such as 60 degrees Celsius or 75 degrees Celsius. You must select conductors with an ampacity that is appropriate for the lowest temperature rating of any connected termination. For example, if the breaker is rated for 75 degrees Celsius and the motor terminals are rated for 60 degrees Celsius, you must use the ampacity from the 60 degrees Celsius column in NEC Table 310.15. D16. Fifthly, consider the type of motor and its application. Some motors, such as those used in variable frequency drive systems, may require special considerations for conductor sizing and insulation. Consult the motor manufacturer's recommendations and relevant NEC articles for specific requirements. Sixthly, consider the presence of harmonics. Harmonic currents can increase the heating in conductors, especially the neutral conductor in three-phase systems. If harmonic currents are present, you may need to increase the size of the neutral conductor or use a specially rated conductor. Seventhly, consider the type of raceway or cable used. The type of raceway or cable can affect the conductor's ability to dissipate heat. For example, conductors in a conduit buried in the earth will have a different ampacity than conductors in a conduit exposed to the air. Refer to the appropriate NEC tables and articles for ampacity adjustments based on raceway type. Eighthly, consider future load growth. If there is a possibility that the motor load will increase in the future, it is wise to select conductors that are sized to handle the increased load. This can save you the cost and hassle of replacing conductors later. Ninthly, consider the environmental conditions. Conductors exposed to corrosive environments may require special insulation or coatings to prevent degradation. Tenthly, consider the accessibility of the installation. If the conductors are difficult to access, it may be wise to select a larger conductor size to reduce the likelihood of future maintenance or replacement. In summary, selecting the appropriate conductor size for a motor circuit involves a comprehensive assessment of various factors, including the motor's full load current, ambient temperature, number of conductors, voltage drop, termination temperature rating, motor type, presence of harmonics, raceway type, future load growth, environmental conditions, and accessibility of the installation. Always consult the NEC and other relevant standards for detailed guidance and consult with a qualified electrician for any electrical work.